Alright children, welcome to the next wonderful lesson we're going to do, and that lesson happens to be section 1.4, Extrema and Average Rates of Change. This educational experience is brought to you by your eminence of Extrema, that'd be me, Mr. Faust. So we're going to take some notes on what it means to be Extrema and different rates of change. So we do have some definitions we need to go over first here. So we talked about some of this before in section 1.2. But to give it a little more formal definitions, alright, a function f is increasing on an interval if and only if at any 2 points there's a positive change in x results a positive change in f of x. Well, what the heck does that mean? It's simple. It's for every x that I have. If I move to the right, my y goes up. So as x goes up, y goes up. So these are some fancy definitions. This can be found in your book if you were a little curious about what that looks like on page 34. So on page 34 you can find all this stuff. Now that's increasing. We also then have decreasing. So what decreasing means is you can see the picture over here. Decreasing, as your x's get larger, your y's get smaller. Or as you move from left to right, your y values are decreasing or getting smaller. And then we have constant function, like you see in the interval right over here. As I move from left to right, there is no change in y. So no change in the y value. So, or f of x if you want to think of it that way. So we've got increasing, we've got decreasing, and constant. Now, a function might be doing this all. It might be doing all of this at once. It might be doing some increasing, then it might be doing some decreasing. It might stay constant at some points. It could have all of these elements in it. Now, my function could also have the following items as well. Okay, a relative maximum of the function is the greatest value f of x can attain on an interval. Now here are the symbols definition. If you really wanted to look at that and get really technical, you're more than welcome to. But for us, what that means in particular is the following. And this can be found on page 36. All it's telling us is if it's a relative maximum, it's bigger than everything else around it. So that's a relative maximum. We also could have a relative minimum. But before we get to that, if a relative maximum is the greatest value a function can attain over the entire domain, it's an absolute maximum. So what does that mean? It means this. Let's say, for example, in the room right now, I have the most education. Why? Because I'm the only one in this room. Now, I am a relative maximum of education right now in the room. Do I have the most education in the building, however? No. You have Dr. Marchini, Dr. Early. They have more education than I do. So while I have a relative max in my little domain of my classroom, I don't have the absolute maximum of my function of school. There's a difference. So if you look at the graph here, look at this point A. A is a relative max because it is bigger than everything else around it right there. But f of b is the absolute max because it's bigger than everything else on this function. So you might be the biggest, baddest person in your little area, but you're not the baddest person overall. Now, as I alluded to earlier, we have relative maxes. We also have relative minimums and absolute minimums. So what that means is you could be a relative minimum, like this point A here. See how it's lower than all the other points around it? That's a relative minimum. It's a little interval there. However, the absolute minimum is f of b, because that's the lowest point on the entire function. So, you may have a relative min or a relative max, but that might not be the absolute min or max, but we still denote them. So you could have these four qualities there. So just because it's a relative max or a relative min does not mean it's the absolute min or the absolute max. Now, before we do a bunch of examples, we need to cover one other thing. And that other thing is average rate of change. So, the average rate of change between any 2 points of the graph of f is a slope. So, I want to know what the rate of change is on a curve. We can find that. Now, you can't read that. That's m of SEC. That's our secant line, which is the red line over here. Now, folks, this might seem like a lot of mess, but all it really is we're finding the slope. This is slope. In a nutshell, this is us finding slope. So this is pretty straightforward. It's our slope equation. y2 minus y1 over x2 minus x1. That's all it is, except we use the fancier definitions of f of x2 and f of x1 and m of this secant line, but all it is slope here. So if I give you 2 points, you find the slope of that line by simply taking our x values, putting our x values into our functions to find our y values, and then doing the slope equation. So now that's over with. Let's hit some examples of some of the notes we have done so far today. Okay, so in this example here, use intervals to tell me where the function is increasing or decreasing. So I have this, and I gave you a piecewise function. So let's talk about increasing. So as I move from left to right, what's the function doing? So if I move from left to right here, this blue line is coming up from negative infinity all the way up to here. That's increasing. So I move from left to right, my y values are going up. So I am increasing from the following values. I'm increasing from negative infinity all the way up till I hit this point here. This point at x equals 2. Right there. At that point, I stop increasing. Now, do I include that point? Sure as shooting do, because it's an included value there. Now, from here, I jump to 0, and I go from left to right. I go down till I hit right there at 4. So that is decreasing there. Because I move from left to right, my y value gets smaller. So I am decreasing from my point 0 all the way up till I get to 4. And I include 4 because it's a point on my graph that I can obtain. Now, look here. From there, I start moving up this way. That's exciting. So that goes back to increasing again. So I increase from 4 to infinity. So as I move from left to right, I'm increasing, stop. Stop increasing. That's my negative infinity to negative 2. I then go to here. I'm decreasing on that little chunk right there. This is why I get 0 to 4, because 4 is my x value. And then from 4 to infinity. Now, if you wanted to get even fancier, we can look here, and I can go, all right, what is a relative max? I'm going to call it an RM. Here's a relative max. Why? It's a bigger point than all around it. And here's a relative max. Bigger than all points around it. Are they the absolute ones? No, because I can find points like here, I can find points bigger than it. Where's a relative min? A relative min is right there. Why? It's smaller than all the points around it. Is it the absolute? No, because I can find points over here. My arrow goes down to infinity that make it so it's not an absolute. Speaking of those relative extrema, let's do an example with that. So estimate and classify the extrema of the graph of the following functions. So there's my function. So I want to classify the extrema. Find out what the point is. So we look right here. This point right there. That seems like a minimum. A relative minimum. Why is that? It's smaller than all our points around it. So I just simply say that. So a relative min at, what's my x value there? Why, it's negative 1. And what's my y value? So there's my point. X equals negative 1. I put the y in. Look at my graph there. I get 4. Negative 4. What's a maximum? Do I have one? Right here. So, roughly, a relative max pardon my terrible handwriting there. A relative max at x equals 1. And my coordinate there being 1, 4. Now, are these relative maxes and mins absolute? Are they the biggest of this entire function? No. See how my arrows here go down and go up? That's a relative max. I can find points over here that are going to be bigger than it. This is my relative min. It's not the absolute because I can find points over here that are going to be greater than it. So there are no absolute mins or maxes. That can happen. So sometimes something might be the biggest, baddest one around it, but it's not going to be the overall champ. Alright, now here's a tricky one. Use intervals to tell me whether the function is increasing or decreasing. Where? And we have this function over here. So, let's move from left to right. I'm going to go from negative infinity all the way up to right around there at x equals 6. What is this function doing while I'm doing that? Why, it's increasing. Because as I move from left to right, my function is growing. So it's increasing from negative infinity to 6. Now, some people in here use open intervals. I use the closed ones. I'm including that point. It doesn't really matter which ones you end up using, to be honest, for increasing and decreasing. They just want the intervals there. Now, I go from 6, I go down forever there. Alright, so I'm going down forever. Then I hop up here. And I still move from left to right, and I'm still decreasing. So, you got one of two options here. It's obviously decreasing. As we can see there, because I move from left to right, my function goes down. Some people like putting from negative 6 to negative 4, and then from negative 4 to 0. They like putting that gap because there's an asymptote here. It's up to you. Some people do it as 1. You will see it written either way. A lot of times people do split it up because they get in the habit of splitting up with the asymptote. So that's what I would suggest. So because as I go from 6 down here forever, as I go to negative 4, and I hop back here, I'm still decreasing. It's one of those infinite discontinuities we talked about. And then from 0 all the way up to infinity, that's where I'm going. That's for increasing. So you've got a lot to take in here, but now you are ready to tackle the homework for this section. So that's a pretty exciting thing. So you can access the homework and begin. Oh, happy days are here again.